Hey everybody, it's Ripley back again. We're going to talk a little bit today about something called improper integrals. Well, what is an improper integral? Is it an integral that shows up at a party wearing white shoes after Labor Day? I doubt it. What it really is it's an integral either taken at infinity or where one of the limits is infinity, or an integral where one of the limits crosses over vertical asymptote. For example, if I have the integral from 1 to infinity of 1 over x dx. Okay, so what are we doing here? We've got 1 over x. We all know what that looks like, right? Looks like that. And you're like, wait a sec, why are we even doing this? How would we ever get a number, right? Is this thing going to converge, or is it going to diverge? Converge means, does it head to a point, or does it diverge? Does it blow up and go to infinity when I add up all these little values? Another example would be like 1 to infinity of 1 over x squared dx. Is this thing going to converge? You may use this shorthand whenever you want now, or does it diverge? Another example of an improper integral would be the integral from 0 to 2 of dx over x minus 1. Since the function 1 over x minus 1 isn't defined at 1, and we're going from 0 to 2, we're passing through the asymptote, that vertical asymptote. So these are the two types of improper integrals. Now, let's deal with these guys first. Okay. Now, I know that this probably smacks as being like, why are we doing this? Why would they ever converge? Well, recall from pre-calculus. Remember that if I went 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot 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 plus 1 over 2 to the n. Remember that this thing, as n went to infinity, remember that this thing converged. If you recall, this converges to 1. Right? The way that we remember that is it's geometric, so it converges to the first term over 1 minus the common ratio, and the common ratio is just the thing that I multiply by the last term by to get to the next term. So this is 1 minus 1/2, which is a half over half, which is a 1. Right? So we're allowed to add up an infinite number of things, and they still head for a value. Right? We know that. A similar situation is like 0.9 repeating. We know that that is equal to 1. Right? Because it's, 9/10 plus 9/100 plus 9/1000 plus 9/10,000, etc., and we know that that thing converges to 1, right? Through the same process as we did here. The question is, if I'm integrating an area, will I get the same thing? Well, just for giggles, I got an idea. We know what 1 over 2 to the x looks like. I know if f of x equals 1/2 to the x. I know that this looks like this. This is the point 0, 1, right? And we know it goes like that. Oh, that's an absolutely horrific drawing. You're going to have to bear with me. Now, the analogy that I use with this, and I'm going to say this over and over again, is think of it as a garden gate. Think of the function as a garden gate. Is the garden gate closing down on the x-axis quickly enough so that the tiny little values that we're adding up for 1/2 to the x don't matter? They're not big enough to suck the entire value up to infinity. Because if it does that, then it converges. If the garden gate doesn't close quickly enough and you're allowing too many values to be added in there, then you have a divergent improper integral. So let's do this one. We're going to do this right now. We're going to take the integral from 0 to infinity of 1/2 to the x dx. Now, this is very technical insofar as you need good technique with this. Theoretically, you are not allowed to talk about infinity as though it were a number. You're not allowed to do that, mathematically speaking. It's like a mathematical ain't got no. But in your brain, you're going to be thinking about it as though it's the number infinity. And we've been plugging in infinities for a long time, right, when we took limits before, which is exactly the tool that we're going to use when we do improper integrals. Watch how this works. I'm simply going to write the limit as t goes to infinity of the integral from 0 to t of 1/2 to the x dx. What we're doing is we're simply saying, all right, we're not allowed to talk about infinity, blah, blah, blah. So I'm going to take the limit. I'm going to let t go to infinity. Ripley, why aren't we allowed to talk about infinity? Because it doesn't exist. I can't stand on the real number line. So I have to, I have to take a limit as I head for that value. Okay, so watch how this works. Limit as t goes to infinity. What is the antiderivative of 1/2 to the x? Well, it's 1/2 to the x divided by the natural log of 1/2. If you wanted to clean this up, you could rewrite this as the negative natural log of 2 as well. And this goes from 0 to t. This turns into the limit as t goes to infinity of 1/2 to the t over the natural log of 1/2, which is just a constant, right? Minus 1/2 to the 0, ooh, that's cool, over the natural log of 1/2. 1/2 to the 0 is just 1, right? So what happened as t goes to infinity? Well, 1/2 to the infinity goes to 0, doesn't it? Isn't that the limit? As t goes to infinity, this thing just goes to 0 because 1/2 raised to the infinity is a teeny, tiny, tiny, teeny number. So this number drops out, right? And I end up with, well, this is negative 1 over the natural log of 1/2. You may be saying, wait a second, Ripley, how is this thing allowed to be negative? This function lives above the x-axis. Ooh, I'm going to get tricky. If you recall that the natural log of 1/2 is the negative natural log of 2, I can factor that out. So this ends up being 1 over the positive natural log of 2. Remember, natural log of 2 is about 0.69 or so. All right, boom. Hey, guess what? This converges. This is a convergent improper integral. Let's do each one of these. Stumble over here. I don't like this color. I'm going to go with blue now. I'm going to take the integral from 1. I could go from 17. Let's go from 17 to infinity of 1 over x dx, right? So we know what that looks like. It goes shoop, and then over here at 17, what I'm doing is I'm taking the integral from 17 all the way out to infinity. The question is, does 1 over x, this function is, this is 1 over x, does this garden gate, does it slam down on the x-axis quickly enough so that the numbers that we add in there are arbitrarily small? They can't add enough to it to make it blow up. Now, some of you might be saying, well, Ripley, what if I went from 0 to 17? Would that be an improper integral? The answer to that would be absolutely it would be. All right, but that's beside the point. All right, so this is an easy one. All I'm going to do, I'm going to take the limit as t goes to infinity, the integral from 17 to t of 1 over x dx, excuse me, and this is equal to the limit as t goes to infinity of the natural log of the absolute value of x from 17 to t, and this turns into the limit as t goes to infinity of the natural log of t, the absolute value of t, of course, minus the natural log of 17. I don't have to put the absolute values, but I will anyway. Now, what does the natural log look like? Oh, the natural log looks like that. It blows up and goes to infinity. So this is actually infinity minus the natural log of 17, which is infinity, which implies it diverges. Well, crud, that's a bummer. Well, how about we try the integral from 1 to infinity of 1 over x squared dx. Let's see if that converges or diverges. Again, it looks very much like 1 over x squared, but it does lock down on the x-axis a little faster, doesn't it? It looks more like that instead of this more symmetric inverse rational function, right? Looks like that. So let's see if it works. Well, this is equal to the limit. Before you take an integral, you've got to go through these steps. I know it's a pain in the butt, but you really do have to speak the language of mathematics correctly. The integral from 1 to t of 1 over x squared dx. And this is equal to the limit as t goes to infinity of, now what is this? This would be negative 1 over x, right? Because the derivative of 1 over x is negative 1 over x squared. So the antiderivative would be negative 1 over x. And this is from 1 to t. So this becomes the limit as t goes to infinity of negative 1 over t, ooh, that's looking good, minus negative 1 over 1, right? As t goes to infinity, we know that 1 over t, this term goes to 0. So the answer to this is just 1, which is convergent. Hey, wait a second. What the heck? 1 over x diverges. 1 over x squared converges. So what about if I took the integral from 1? Again, this 1 is kind of arbitrarily chosen, right? If it's going to converge from 1 to infinity, it's going to converge from 0.5 to infinity or 15,000 to infinity, because we know the part that's trouble is the infinity part, right? It's not where we started. All right. Now, if I integrated from 0 to infinity, I would have problems. I would have to bust this thing up, wouldn't I? So what if I took the integral of 1 to infinity, from 1 to infinity, of 1 over x to the p. I'm really interested to see if this p-value, the p-value clearly matters, doesn't it? Because when there was a 1 there, divergent. Meh. When there was a 2 there, convergent. Huh, interesting. So let's take the antiderivative of this and see what happens. Well, first things first, let's take the limit as t goes to infinity of the integral from 1 to t of, now I'm going to rewrite this as x to the negative p just for a second, okay? Just so it'll make it easier to take the antiderivative of it. Now, this is going to turn into the limit as t goes to infinity of, now, remember, this is easy. This is an x to the n, right? So this is going to be negative p plus 1, right? Because that's what the integral of x to the n is. So I'm going to rewrite this as x to the 1 minus p, which is the same thing as negative p plus 1, divided by 1 minus p from 1 to t. And let's take a gander. So I'm just going to keep on writing over this way. So this becomes the limit as t goes to infinity of what? T to the 1 minus p over 1 minus p minus 1 over 1 minus p, right? Because if I plug a 1 in, 1 to the anything is 1. True? All right, now let's think about this for just a second. A couple of things are going to happen here. I'm going to use my red as a warning. Do you agree that if 1, there are two cases here. Let's go case 1. Let's go 1 minus p is greater than 0. Now, you probably see that if 1 minus p is greater than 0, that implies that p is less than 1. True? If p is less than 1, if p is less than 1, well, what happens? Well, doesn't this imply that the limit as t goes to infinity of t to the 1 minus p, if it's greater than 0, then I have infinity raised to a number that's greater than 0. If you let infinity be raised to any number greater than 0, then we are definitely going to diverge. There's no doubt about it. Because infinity always wins. You might say, but Ripley, what if it were just like, if 1 minus p was like 0.0000000000001? Infinity doesn't care, right? It's such a huge number that we would still blow up and go to infinity. So if p is less than 1, we actually know that if p, this whole thing implies that if p is less than or equal to 1, because we proved over here that it's divergent, then the integral from 1 to infinity of 1 over x to the p dx will diverge. Now, case 2. Let's see what happens with case 2. What if 1 minus p was less than 0? Well, again, this would imply, oops, sorry guys, this would imply that p is greater than 1, right? Do you agree? Well, then the limit as t goes to infinity of t to the 1 minus p. Now, if this is less than or equal to 0, then remember this whole thing would kick into the denominator, right? You agree with that? Remember, 1x to the negative a is equal to 1 over x to the a. So I would have infinity in the denominator. In other words, this would equal 0 because infinity is in the denominator, which implies I would just get negative 1 over 1 minus p. True? Oh, you know what? I did a bad thing. I'm supposed to have a 1 over 1 minus p out here, aren't I? No, I'm not. Never mind. Don't listen to me. I did a great thing. I am awesome. Sorry. This implies that the integral from 1 to infinity of dx over x to the p converges. Guess what? We have a very, very powerful tool that's going to show up again later when we talk about sequences and series, and that is simply a p. This is called a p integral. And the p integral is the integral from 1, this is arbitrary, right? It could be 70,000, it could be 93, who cares? The integral from 1 to infinity of dx over x to the p, that's raised to the p. It will converge if p is greater than 1. It will diverge else. That's a super powerful tool. You need to know that. Okay? All right, cool. Now, let's do a couple more things. Don't get speedy on me. Let's talk about that other one that I did. Let's make it interesting though. Let's take the integral from 0 to 1 of 1 over x minus 1. Whoops, let's go integral from 0 to 2 of 1 over x minus 1 squared dx, right? Well, what would I do in this case? Well, I would bust it up into two integrals. I would go the integral from 0 to 1 of 1 over x minus 1 squared, right, dx, and then add that to the integral from 1 to 2 of 1 over x minus 1 squared dx. I'm not going to bore you with the gory details, but I am going to show you how to set it up. I would take the limit as t goes to 1 this time of the integral from 0 to t of dx over 1 minus, try this again, of x minus 1 squared, and I would add to that the limit as t goes to 1 of the integral from t to 2 of dx over x minus 1 squared. And then we go through the exact same thing. Okay? Now, there's not a whole lot to this. It's pretty simple. The nasty part is when we have to bust this up and start taking limits. So be careful with your limits. That's really, really important. Now, there's one more thing that I want to talk to you about that should be incredibly intuitive, but I have no idea what just happened. But we need to take a minute. And with that, I need to take a break. I got to go to the little boys' room. So I'm going to sign off for a second. I'll be back. Sorry about the hard cut, but I'll be back in just a second. We're going to talk about the comparison test. So we're going to use the comparison test. And this is probably going to be your first kind of robustly theoretical way to deal with some integrals, all right, where we actually will use this tool not only in improper integrals, but in sequences of series. Okay, I'll see you in a second. All right, so let's talk about the comparison test. Comparison test is absolutely straightforward. It simply says this. It's kind of a little theorem. This is actually the comparison theorem. It says, suppose that for all values, whoa, that's weird, values of x on the interval from a to infinity, that f of x is greater than or equal to g of x. Okay, so that's what we start with. All right, so, and we're going to say and. Now we're going to have two different scenarios here. And one, the integral from a to infinity of f of x dx converges. Now think about that. I've got two functions, all right? F of x is always greater than g of x, right? So this guy right here is f of x, and that's a terribly drawn coordinate axis, but you're going to have to bear with me. And here's g of x. It's always less than or equal to, so this guy here is g of x. Now if f of x converges, right, and g of x is underneath, oh, wait, by the way, I missed a little something here, which you're probably all like, wait, what? This is also greater than 0. It's got to be positive, because otherwise g of x could dip down to negative infinity. So too could f of x, although we did say that it converged. All right, so if g of x is wedged between the x-axis and f of x's garden gate swings shut quickly enough to make it converge, then what does that say about the integral from a to infinity of g of x dx? What's got to happen? It's got to also converge. How about this one? What if the integral from a to infinity of g of x dx diverges? Now we got the same situation. All right, here's g of x. G of x is always less than or equal to f of x. And g of x's garden gate does not shut quickly enough, right? What does that say about the integral from a to infinity of f of x dx? Well, you're like, well, duh. Then it's got to diverge. Now, you may be saying, well, what happens? What if, okay, f of x is greater than or equal to g of x for all values between a and infinity, right? And g of x converges. What if g of x, what if the integral, so let's go 3, the integral from a to infinity of g of x dx converges? What does that imply about f of x? What does that imply about the integral, of f of x dx? Well, that's a big fat question mark. Likewise, excuse me, if the integral from a to infinity of f of x dx, this would be scenario number 4, what if it diverges? Well, f of x's garden gate may not have closed quickly enough, but g of x, we don't have enough information about g of x. So what does that imply about the integral of g of x dx? Well, again, not enough information. All right, now let me give you one example of this because this is really important that you see how I want to see this written out. This is super important. So I'm going to take the integral from 2 to infinity of dx over x squared plus 5x minus 1. All right? Now, it smells a little bit like 1 over x squared dx from 2 to infinity, doesn't it? Which we know does what? What do I know about the integral from 2 to infinity of 1 over x squared dx? Well, we know it converges. Why does it converge? Because p, I could either say, is greater than 1, or I could say that p equals 2. Either one of those suffices because it's a p integral. All right, but I don't have that. However, watch what I'm going to do. Hopefully everybody agrees that x squared plus, I would write, we know x squared plus 5x minus 1 is greater than or equal to x squared on the interval from 2 to infinity, right? You may say, wait a sec, what about that minus 1? Well, guys, 2 squared is 4, plus 10 is 14, minus 1, that's bigger than 4, all right? So it's gonna be that way forever, all right? This implies that 1 over x squared plus 5x minus 1 is less than or equal to 1 over x squared, right? Because I took the reciprocal. Remember, when you take the reciprocal of both sides of an inequality, the direction of the inequality reverses. Now, since the integral from 2 to infinity of 1 over x squared dx converges, why? Because p equals 2 or p is greater than 1, it doesn't matter. This implies that the integral from 2 to infinity of dx over x squared plus 5x minus 1 must also converge by the comparison theorem or comparison test. You have to do all of these steps. All right, you can't just say, well, since we know this, we've got this. No, 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 no. That's the conclusion. You have to build the case first. I refer to this as lawyer math. You are building a case, and then it's like, oh, at the end, bam, I know 1 over x squared converges because p equals 2. Therefore, because of the case that I have built, I know that this also converges by the comparison. Excuse me, theorem. All right. That's it. That's it for this section. You're going to get lots of practice with these. Don't worry about it. And the cool thing about 7.8, it is so applicable and so useful when we start talking about sequences and series, which is arguably one of the harder chapters of all of Calc 1 and 2. So you build a strong base in improper integrals, and you are going to be really, really happy with what happens in sequences and series. All right, thanks for your time and attention. Have a glorious day, and I will see you tomorrow.